All right, guys, so today we're talking about memories. All Alone in the Moonlight. Has the moon lost its memory? I don't know. All right. So let's talk about memory. And specifically, we're going to be talking about this memory. Okay. So pointers in C are just really an integer. We've talked about this before, right? It's just a memory address. The trouble with this is that we use pointers for three different things, and we can't tell from the type. C pointers suck because the type doesn't include the following information. Question number one, do we own the memory? i.e., should we delete the memory when we're done with it? Right? So ownership. So if you have an int pointer here named, I don't know, Putter, as Arthur Dwyer mispronounces it, or pronounces it, I don't know what's correct. And we say new integer, and we're going to initialize this to value 42, and we see out the value pointed to by that pointer. What number are we going to get? No stream in Discord. Oh. I see. There we go. How about now? All right. So let's pull that back up for you guys. So if I knew an integer, is this allocated off of the stack or is this allocated off of the heap? Is the stack allocated or heap allocated? Correct, it's heap allocated. Okay. So what number is this going to print? So I have allocated 4 bytes. Heap allocated 4 bytes. 4 whopping bytes of RAM have been allocated. And we print out the value at that memory address. What number are we going to print to the screen? What do you guys think? What's wrong with this code? It will print 42, sure. What's wrong with this code? What kind of memory mistake did I make? No delete, right? So I need to delete Putter once I'm done with it. And now my code is correct, and if I run it with address sanitizer f ties equals address and SCC, run it, I get 42, no problems. If I don't delete it, then I'm going to get should have shown a memory leak on that. Interesting. Yeah, that's a memory leak though. Okay. So there is this intangible metaphysical property that is also passed out when you knew something, and that is called ownership. So when you knew something, you are contractually obligated to delete it, right? This is metaphysical ownership is acquired here. And I say it's metaphysical because it's not actually in the code anywhere. And this is why C pointers suck. There's no indication if the pointer that I have is the owner of the RAM, which means it's my job to delete it, or if I don't own it, in which case it would be wrong for me to delete it. Okay, so let me show you a problem. All right, so we've got this function here called foo. It takes in an int pointer like this, and we're just gonna scoop up the data here and pass it in here. Okay, and we say foo pointer. Is my code correct? We got one new, we got one delete. The metaphysical ownership is being passed to foo here. And then foo, because this is because we own it, we must delete it when we're done with it. That's what ownership means. It means when we're done with it, we have to free the memory. Okay. Should be correct. All right, should be right. Am I in insert mode? What is this? Okay. Seems fine. Okay. What about this? What about this person here? Integer Bob is equal to 66. Is this stack or heap allocated? Okay. So when you stack allocate something, there's no new, there's no delete. If you delete a stack allocated variable, you're doing it wrong. It's a seg fault. If you do nothing with a stack allocated variable, it unallocates itself at the end of the scope that it's in. So right there on that highlighted line, Bob will automatically free up the memory. I don't need to do anything. So let me present you a problem. What's going to happen now? So we are passing a pointer to Bob. It's going to print 66. No, probably change that. It'll print the value pointed to by Putter. What is this line going to do? What's going to happen? Do you think address sanitizer is going to be particularly happy with us deleting a stack allocated variable? Remember, delete only works with allocations off the heap. It does not work with stack allocated variables. What do you think it's going to? You think it's going to be mad? I think it's going to be mad too. Let's find out. Boom. Attempting free on address, which was not malloc. Malloc is the C version of new. So it's mad. Okay, it's mad. We are. This may be a false positive. You have some custom stack unwind mechanism. Yeah. No, we're not. We don't have anything. We don't have any. Nothing custom here. We just screwed up. So put yourselves in the shoes of the person writing foo. Do I delete Putter or not? The heap is the manual version of the stack. Is a perfectly acceptable way of thinking the heap, except the stack is like it builds up and then unwinds. The heap you can sort of allocate and unallocate as you will. It's not like a first and last out relationship. But yeah. You got to do it manually. Manual allocations of memory, manual deallocations of memory. Should this line of code be here? That line right there. Should that line of code be there? Which way is more correct? To have it in or to not have it in? How do we write foo so we never segfault? We can't. There is actually no way for us to write this function correctly. Based on what we know here, we don't know if we're supposed to delete it or not. We could put in a Boolean or something, right? Be like bool is owner equals false. By default, we're not the owner, but if is owner is true, then we'll delete it. This is probably the best we can do. And then for this guy, we'll pass it true. And now we're good. Okay. But here's the thing. What if the person calling us lies? We can't tell. All right. Oh, look, we memory leaked. We did not delete something we were supposed to delete. Right? Over here, if we put in a true there, oh, we deleted something we weren't supposed to delete. Okay? You guys see what the problem is? From the type information, from what we know about Putter, we cannot tell if we are the owner of that memory or not. They both look the same to the type system. That's why I'm calling it a metaphysical property, because you as the programmer have to keep track. I'm owning this. I'm not owning that. You know, what if we copy the pointer, right? Like, what if we say like int pointer2 equals pointer? Now we got 2 copies of it. Which one's the owner? Which one's not the owner? You know? I don't know. I don't know who the owner is anymore. They're both the owner. If they're both the owner, then this is going to cause a problem, right? Because they're deleting. It's not good. It's not good. Ah, double free. Fa 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 fa. Double free. Use after free. Actually, it's also a double free. I don't think we got that far. But look, we're trying to delete it twice now. Do you guys see how this is a really pernicious problem? And the type system, it would be really nice if the type system, like if there's a type of pointer called like owning pointer or something like that, or owner or something like that, where you could tell I'm the guy who has to call delete on this when we're done. And in fact, there is something called the, what's it, GLSL owner pointer. What is it called? The guidelines, GSL guidelines. GL shader language is different. Yeah, so there is an attempt to make a new pointer class called owner that would contain that information. And if you ever dropped an owner, like if you ever had a function that took an owner, you either have to delete it or you have to pass it back out when you're done with it. But unfortunately, that's not part of the core language. It's part of something called the Guideline Support Library, the GSL, and nobody uses it. So, I mean, I'm sure, like people that are in the know use it, but you know what I mean? Like it's not widely used. And even still, that's kind of like working around the problem a little bit. It would have been nice if that was in the language from the beginning. Would have solved so many problems. Okay, so many problems. This is basically basically an unsolvable problem. If you're the person writing foo, you have no way of guaranteeing correctness of your code. That your code's never going to explode because you can't tell if you're owning. That's problem number 1. Problem number 2. How many are we pointing at? Is this pointing at 1 integer? Or is it pointing at 10 integers? We're writing foo. We can't see main. How can I tell if this is pointing at 1 integer or 10 integers? What do you guys think? Anyone? How can we tell how many we're pointing at? Size of values at the pointer? Well, let's see if this will work. Let's fix this up a little bit. So, that should be false. Okay, so the code is correct now. Let me just double check that. I broke it any number of different ways. Okay. All right, so let's make an integer array. Everybody say R in chat. R. Good. Cool. So check this out. I've got an integer array. Integer arrays are what? They're pointers. Notice there's no type conflict here. The reason for that is because an array instantly decays into a pointer the second you look at it or sneeze it or try doing anything with it. All an array is the beginning of a block of memory. In this case, 200 bytes of memory. Every integer is 4 bytes. There's 50 integers. We just allocated 200 bytes. Is this off the stack or is this off the heap? Stack. Good. Stack allocated. The only time it's going to be heap allocated is if you got a new in there somewhere, right? Or you're calling a function that's doing something. Yeah, stack allocated. So this guy is going to get deallocated here automatically. If we try deleting it, we're going to get the same problem. But there's a different problem, which is we want to print all the values in the array. And this is only going to print the first one, which is going to be 10. Okay. So we need a for loop here, right? We need to say for int I equals 0, I is less than something I++. So we're going to print the value pointed to by putter and then move to the next element in the array. How many elements are being passed in here? Can we tell from the type information if we are pointing at 1 int or 50 ints? Nope, we can't. It's exactly the same type. The type system is utterly insufficient here. It sucks. Okay? This is why they suck. You don't know if you own it. You don't know how many elements you're pointing at. And we'll get to the third issue in a second. Okay. So we typically will resolve this problem by passing in like integer n, equals 1, and just passing in, the size, right? Passing the size. And I need to close parentheses, of course. And now down here, we have to pass in. We are doing 1 integer here. We're doing 1 integer here. We're doing 50 integers here. Yeah. And we're trying to delete something that wasn't allocated. What are we trying to delete now? That's a false, isn't it? How are we deleting something? That should be deleted. Shouldn't be deleted. Shouldn't be deleted. What's going on here? Line 19. Line 19. And it's being deleted on. It's being deleted on line 14. Okay. How do we just break something? Passing the pointer. Oh, because we're moving the pointer. That's why. Yeah, can't do that. Can't do that. And make it temp, I guess. And pointer temp plus putter. There we go. So we got all the numbers here, right? Okay. And so the third use of pointer is like specifying a range. So we're just sort of observing a chunk of memory. Right? So do you guys remember sort, like vector, sort vector.begin, vector.end, takes in a pair of iterators. It can also take in a pair of pointers, right? So if you have this here, these guys here, let's see, make it a 70 and a 20. Let's shrink it down to 10. Oh, look, here's another problem. Uh-oh, my video's dead. Whatever, minimize. Okay, here's another problem. Look, if I update it in one place and I don't update it in another place, you know what's going to happen? You guys ready for this? Boom. Stack Overflow. Yet another type of... Am I still frozen? I'm still frozen. Literally my face right now. My camera's dead. All right. Well, worry about that later. So, yeah, if you're passing the size, you have to make sure that the size is correct, and you have to make sure that this is correct. And who makes sure it's correct? The person using the code. The person who writes the code has no way of guaranteeing that these parameters are actually going to be correct. It's extremely dangerous. Okay. So if you wanted to sort something, you could say sort from array to array plus 10 if you want. And we need an algorithm for that. And you can see here, we have successfully sorted the array. The array, remember an array is a pointer. And if you add to a pointer, it moves that many elements to the right when you add to it. So when I say array plus 10, that is pointing one past the end of the array. I'm trying to figure out why my camera is not working here. It is just dead, I think. So do you guys understand what I mean by specifying a range with pointers? Like, that's a pointer, and that's a pointer. And so you can use those two pointers to specify the range that you're going to sort. Does that make sense to you guys? I'll just leave this up. The webcam is dead. Okay, so this will just be my expression for the rest of this talk. There you go. You can enjoy that. Okay. So Olson said, so that's not a problem. It's not, right? It's not a problem. Pointers can be used for observing. And that's actually, Bjarne Stroustrup said, there's nothing wrong with a C pointer, right? If you're just using it to say, hey, look at this guy over here, it's fine. The problem is if there's ever any ambiguity of ownership or how many you're pointing at, then you get into trouble. But here's a problem. What if you specify, what if you try and do a range like this? That will compile just fine. You guys see that? There is no guarantee that your range comes from the same object, right? You got one pointer here, you got one pointer here. And you can't, it's okay, but no guarantee they are from the same block of memory. So that's the one gotcha there. So you can't really tell. If you're sort, you can't tell that this is one guy, that's another guy. And so if we compile this, maybe it'll work, maybe it won't. We are in fact doing a Stack Overflow. Yeah, cool. All right. So this is not good. This is good. All right. So address sanitizer is life. Just remember that. Okay, so now that I've kind of convinced you guys that C pointers kind of suck, there's a limited, like I said, I'm kind of on Team Bjarne on this one. Like there's still a use. Like if you're going to pass, just like, hey, here's a guy, go look at him, you want to pass it by, passing the memory instead of the object. It's fine. It's not the end of the world. I'd probably use a reference, but pointers are nullable. So yeah, it's fine, I guess. Let me show you the better way. Okay. C++ has two alternatives to C style pointers. Okay. First is called iterators. They are used for specifying ranges. They also have a problem of, not necessarily coming from the same data structure. But in general, iterators are better than raw pointers because iterators never own. They don't own things. They don't ever own things. They only point at one thing. And they are always used for ranges. Okay? So they are much more specific than C pointers. Because with C pointers, you never know if you own. You never know how many you're pointing at. Really, I mean, they can tell you, but they could be lying. Right? And they may or may not be specifying a range. Right? With an iterator, they're basically always used for ranges or for pointing at, or pointing at a single object, right? It's like if you return a pointer to something in the standard library, it's actually going to return an iterator. And it behaves just like a pointer. You can, iterators can be dereferenced just like a pointer. using the star operator. So you can do star it. So if it is an iterator, that will print out the thing pointed to by the iterator. The other option we have here are called smart pointers, or smart pointers for short. Smart pointers are used to express ownership levels. Ownership, yeah. To express ownership of a chunk of memory. Okay. There's one weak pointers expressly don't own, but we'll get to them in a second. Okay. So there's two types of smart pointers. There is what's called a shared pointer, and there's something called a unique pointer. Shared pointers can be copied, like a regular pointer, and unique pointers, Gus, can they be copied if they're unique? Can you make a duplicate? Do they have a copy constructor? What do you guys think if they're a unique pointer? So you might think, okay, well, shared pointer is better then, right? And to a certain extent, shared pointers might be a little bit easier to use. But most experienced computer science people in C++ will tell you, try to use a unique pointer unless you have to use a shared pointer. Okay. And the reason for that is there's a little bit of a performance overhead with a shared pointer. Not a lot. It's not enough to really make me stay up at nights. But unique pointers are never ambiguous about these questions. Do you own the memory? Yes. Unequivocally. When you have a unique pointer, you own the memory. Period. Done. You own it. Okay. How many is it pointing at? Whatever is in the let me give you an example of a unique pointer. Okay. So instead of all this nonsense here, let me show you how to do this with a unique pointer. We're going to take in a unique pointer named int pointer. And we don't need a for loop anymore because this will only ever take in a pointer to a single integer. Okay? There is no ambiguity. This takes an owning pointer to one int. No ambiguity. A unique pointer with angle bracket int here, it is pointing at one int and one int only. Not an array, one. Okay? No ambiguity. It's in the type. You can look at the type and say, I own that RAM, and I point at one integer. And you have to star to dereference it. Don't need that anymore. And we don't need that anymore. Okay. So let me show you, kitty, meow, meow. Cat came to visit me. So let me show you the coolest thing about unique pointers. By the way, this function is bad because, well, you'll see in a second. So I'm going to make a unique pointer named putter. It's going to be pointing to an F12. What is that? Putter. And I'm going to call the make unique function. And I'm going to say, make me a pointer to the number 42. This secretly calls new. What do you guys think this is going to print to the screen? This string is going to go to the screen. What do you think that's going to print to the screen? This is a heap allocation. This is better than new. Okay. Get 42. Great. Now, what if we try passing this to a function? What if we try passing it to foo? Am I passing in putter by value or by reference? Is this a call by value parameter Or is that a call by reference parameter? It's called by value. Okay. And the thing about a unique pointer is that you can't duplicate it. Okay. So this code will not compile because we are trying to call the copy constructor. The copy constructor has been deleted. Okay. We cannot do this. This is actually a good thing. This is actually a feature. This prevents us from making a copy of our unique pointer. It's actually, you should probably make this const reference. Okay. Just like that. And now it works. Okay. So if we compile our code and run it, everything works fine. Now, question. Do I need a delete? Why am I not getting memory leak? There's a new, where's the delete? I'm not leaking memory. Where's the delete? What part of the unique pointer class do you think is freeing memory? Which function gets called? There is no copy constructor. Can't be in the copy constructor because there isn't one. What is the name of the thing inside of a class that gets called when an object goes bye-bye? The destructor. Remember, choose the form of the destructor, right? Choose the form of your destructor, right? Which is the Stay Puft Marshmallow Man in Ghostbusters. Here's a Trump. Here's a Biden. Okay. All right. So the reason why I don't need a delete, the reason why I'm not getting a memory leak, the destructor calls delete for us. The destructor calls delete for us. So make unique calls new for us. The destructor gets called here, right? Here is where it's going to call, tilde. It's calling that function, right? It's calling it right here. Unique pointers automatically free their memory when they go away. So look at this. There's not a single new in our program. There's not a single delete in our program. So this is a pretty good program. There is a phrase in modern C++, no news is good news. No news is good news. I, generally speaking, don't write code that uses new or delete anymore. The only time you'll see me writing new or delete is if I'm doing something pretty low level, like writing my own vector function, writing my own linked list class, that kind of stuff. Now, you could do your linked list class using shared pointers and unique pointers. I would probably just use a raw pointer because there's nothing in your class that is exposing those raw pointers to the outside world. So as long as you keep everything under the encapsulated functions of the class, as long as all of your messing around with raw pointers is all done inside of the class itself, none of it's exposed to the outside world, it's fine. It's fine using a raw pointer because you can look at your code and be like, I've got one delete for every new, everything's fine, everything's perfectly balanced, it's all things should be. You can, or you can use unique pointers. It's fine. You're going to have a little bit of trouble though with unique pointers because we're doing a doubly linked class, right? You're going to have a problem using unique pointers for a doubly linked list because there's two pointers to the same node, right? They're duplicated, and a unique it will be impossible using a unique pointer because in a doubly linked list you have two pointers, right? You guys understand, you can't use a unique pointer to make this because you've got two pointers that are pointing at the same thing. You have to use a shared pointer. You guys with me? So a shared pointer is going to look like this. This looks awfully similar to the other one, doesn't it? Instead of unique pointer, I have shared pointer. Got a shared pointer up here. Got a shared pointer down here. Got make shared over here. Technically, this could be auto if I wanted. I don't have to repeat myself. That works too. I just changed unique to shared. Yeah. Now, if I did this, this would actually work if I pass it by value. You see that? No problem. Shared pointers can be copied. And the key thing about a shared pointer yeah, okay. Memory, right? Cats. Yes, you're welcome. Sorry, I jump scared myself. Where was I? Oh yeah, shared pointer. The way that shared pointers work under the hood is they've got a reference count. Okay. So yeah, it looks something like this. So it's got a reference count. So every time you duplicate a shared pointer, the reference count goes up by 1. Every time you have a shared pointer go bye-bye, the reference count decrements. And if the reference count ever hits 0, then it frees up all the copies. So like if you were to ask like putter dot use count, I think that's what it's called. You'll see that there are 2 copies of the shared pointer, right? Because you've got 1 copy here, because that's a copy. Call by value makes a copy, right? So that's going to print out, we've got 2 copies of this pointer. One's here, one's back in main. Now, if we did this as we should have done, which is using call by const reference, then you'll see that that drops to 1, right? That's why we could use it with unique pointer, because we're never copying it. And so the way that shared pointer works is that whenever the shared pointer goes away entirely, then it frees up the memory. But you got one problem with that. You got one problem with shared pointers, which is what if somebody decided to remake cats? Yeah. What if you have a doubly linked list and you got a doubly linked list. You got a head pointer pointing at the front. You got a tail pointer pointing at the end. And you set head pointer to null and tail pointer to null. Are there still people pointing at each one of these nodes in the linked list? If you had a singly linked list, it wouldn't be a problem, right? Because if head goes to null, then nobody's pointing at this one, and it erases 7. And then after 7 gets erased, that means there's nobody pointing at 10. 10 gets erased. And so you get a chain domino effect of deletions. With a doubly linked list, if head stops pointing at it, we're still going to have somebody pointing at us from our next node, right? Every node points to each other, kind of like the Spider-Man meme, right? Where they're all standing in a doubly linked list like this or something. They're all pointing at each other. Do you guys see the problem? Like if these were shared pointers, right? It would never get deleted because each person's pointing to everybody's pointing to somebody else. And so you never hit a point where there's no people pointing to you anymore. You guys got it? So when you use a doubly linked list, if you try making out of shared pointers, share pointers, it'll never automatically delete itself. Okay. So there's something called a weak pointer in C++ that is designed to combat this situation. So let's see if we can find a linked list in here. These are all singly linked lists. Not super useful. Okay. So let's say that you're building a doubly linked list using smart pointers. Okay. If everything's a shared pointer, it'll never automatically delete itself. Do you guys understand this? In chat, like tell me. Like if all these guys are shared pointers, then you'll, even if you erase head and you erase the tail pointer, there's still at least one person pointing at every node in the list, and it won't auto delete. You'll leak memory. That's the true hidden danger of a shared pointer. Is it if somebody keeps a copy of a pointer somewhere, then it just won't automatically free memory. Okay, that's why people tend to prefer unique pointers, because not only is there no question about who owns it, there's also the adjacent pointers are still pointing to their friends, and so they won't get deleted. You only get deleted when all of the pointers are set to null. Okay. So the way that we resolve this is using what's called a weak pointer. And a weak pointer, here, let me show you how this works. So we've got a weak pointer here. A weak pointer can be a copy of a shared pointer. So we've got a shared pointer here, and we copy it. That's fine. You can copy a shared pointer into a weak pointer. It's fine. The observe function will say, let's not even look at that. Let's look at expired. That's probably a better way of doing it. Okay, so we copy the shared pointer into this weak pointer here, and we call f. And f can tell us, has that guy been deleted? And when we start off, we're still in the same scope, so this guy has not been deleted yet. So it'll say, yeah, GW is valid. Once we go out of scope, so once we hit this line of code right here, that guy automatically deletes itself because the weak pointer does not increment the reference count. Okay, so every time you make a copy of the shared pointer using a weak pointer, it does not increase the reference counter, and therefore it does not keep it alive longer than it should. But the trouble is you can now have a weak pointer pointing at something that's gone bye-bye. And so there's a function in it called expired that will tell you whether or not it's actually pointing at anything anymore. So here we have the function calling expired, and it's saying, yeah, the guy that we're pointing at has gone away. And so you can avoid dereferencing a dangling pointer. Okay, that's maybe a little bit, it's there for a reason. Okay. And in general, though, when I make data structures, I just use raw pointers. It's fine because I don't, I'm in control of every new, I'm in control of every delete. That's fine. But like I said, when I'm going about my daily business, I never use new anymore. Like just for like random stuff. It's always a unique pointer. 80% of the time, it's a shared pointer. Some of the time, it's very, very rarely that you'll see me use a raw pointer, except maybe in like CSI 40 or something like that when I'm teaching it. Okay. So it keeps track of how many copies of itself exist. And when the reference count hits 0, it will delete the memory automatically. Makes sense? So it's got a little integer. Every time you duplicate a shared pointer, the reference count goes up. Every time a shared pointer goes away, the reference count drops. And when the reference count hits 0, it frees the memory. So, let me show you a bad way of doing this. You'll see some people do it like this. In fact, you could probably even say shared putter int putter2 new int 66. and you'll see we get 42 and 66, and the reference count is 1 for each one. So you'll see people write code like this sometimes. This is not advised. Make shared is the correct way of doing it. The main difference being, if you call new like this and you throw an exception, then what will happen is it'll new the memory, and then it throws and it goes up to it just immediately bails out of the function. And so it never actually finishes making the object. The object doesn't get destructed, so it never frees the memory, and you will leak memory. So this will work. Like this, the code's fine. It's just if you're in a situation where the thing you're newing can throw an exception, then you could leak memory feasibly. So this is the best way of making a shared pointer. Again, I would probably just use a unique pointer for all this. So let me put this back on unique. That's what I do here. Okay. Any questions about this code? You're going to see these in your Milestone Project 2. So your Milestone Project 2 uses the make unique function. And the reason why we do this is because the Milestone Project 2 uses inheritance, which is our topic for the lecture on Friday. So that's why I wanted to introduce this first, so you understand make unique, which is just better, right? So depending on what you want, you should probably pretty much all the time not use C-style pointers, except if you're doing low-level stuff, like actually making a data structure or something like that. Even then, you could probably, it's a design decision at that point. So instead of using a C pointer, if you want to just point at something, use an iterator. If you want to range, use an iterator. If you want to own memory, then you use a smart pointer. Okay. There's one last smart pointer, but nobody uses it, so I'm just going to mention this. It's something called auto pointer, and this was old buggy version removed in C++ 17. Okay. So you might see Geeks for Geeks or some other terrible websites like that mentioning auto pointer. It doesn't exist anymore. It was purged from existence. It was deprecated in C++ 11 when these were introduced. These were introduced in C++ 11 as replacements for auto pointer, and then it was actually deleted from the standard in 17. So if you ever seen this, just ignore it. Use one of these things instead. Okay.